Welcome to this technical tutorial. Today we'll cover how to fine-tune RF-DETR keypoints on your own data and train a keypoint detection model of your own. This is a hands-on tutorial from the Roboflow blog. We break it into 4 steps and walk you through each one. First, let's understand what RF-DETR Keypoint actually is. It is a real-time transformer model for keypoint detection, extended from the RF-DETR architecture. Its biggest feature is predicting both bounding boxes and keypoint coordinates in a single forward pass, requiring neither NMS post-processing nor a pre-generated heat map. It has 4 core capabilities. First, a single forward pass outputs both bounding boxes and keypoints. Second, no NMS, fully end-to-end with no post-processing. Third, no heat map, it directly regresses coordinates. Fourth, every keypoint carries an uncertainty ellipse derived from the covariance matrix, telling you how uncertain the model is about its own prediction. Let's ground this with a concrete case. The dataset is basketball court detection, annotated with 33 court landmark points such as intersections of various lines. Once trained, its goal is to map the court into a 2D tactical board for game analysis. The overall workflow has 4 steps. Step 1 runs the COCO preview checkpoint to validate the pipeline. Step 2 builds the COCO keypoint dataset. Step 3 chooses a training method, no-code platform or open source, your choice. Step 4 evaluates metrics and deploys inference. Let's expand on each point. Let's look at steps 1 and 2 first. In step 1, run RF-DETR Keypoint preview on a sample image to get instance boxes plus 17 body keypoints, confirming the pipeline works. In step 2, annotate in Roboflow with 33 points placed at precise geometric positions, then export the COCO keypoint JSON file. Step 3 offers 2 training methods. On the left is no-code training on the Roboflow platform. Pick the RF-DETR preview large model, set up pre-processing, and click Train, ideal for quickly validating an idea. On the right is open-source Python training, fully local and controllable, suited to scenarios needing custom hyperparameters or multi-GPU scaling. Both paths ultimately produce the same set of weights. Let's focus on the open-source paths code. First, install dependencies, RF-DETR plus Roboflow and supervision. Then infer the keypoint schema to get the class name and the number of keypoints per class. Next, set hyperparameters, resolution 576, 50 epochs, batch 2, learning rate 1 × 10 to the power of -4. Finally, call trainer.fit for fine-tuning. For inference, simply load the best weights with from_checkpoint. Step 4 is evaluation and deployment. Training produces metrics.csv, which contains the loss curve and the map curve. The key metric we watch is val/keypoint_map_50_95, which we use to pick the best checkpoint among all of them, checkpoint_best_total.pth. Here's an evaluation tip. When judging keypoint quality, watch the size of the uncertainty ellipse rather than just whether labels overlap. Because occlusions and crops often lack ground truth, label overlap is simply unreliable. Higher confidence yields a smaller ellipse. This ellipse area actually approximates the localization error. Let's look at real-world results. In completely unseen NBA broadcast footage, the model successfully tracked all 33 court points, staying robust even under heavy occlusion. It then maps to a 2D tactical board via homography and can even render player heat maps by combining a tracking model. Finally, let's review the key numbers. The default skeleton has 17 keypoints, the case study uses 33, input resolution is 576, training runs for 50 epochs. To get started, simply fork the official collab and change the download line to your own Roboflow project. Dependencies are RF-DETR, Roboflow, and supervision.